Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we are delighted to welcome Limin Yao to MSI Redmond for a couple of days. She is finishing up her PhD with Andrew McCallum at UMass, and today she's going to talk about universal schema.
Thanks for the introduction. Thanks for having me here. Today I will describe a universal schema for knowledge representation from text and structured data. So entities and the relationships among them are central for representing our knowledge about the world. So my research goal is to extract relations from text and structured data. So given a collection of documents, we may find sentences like Peter McLaughlin, the president of National Football League Seahawks. So from these sentences, we can identify entities. For example, we identify these entities, Richard Samuels, MIT, Peter McLaughlin, Seahawks. So what is our task? So our task is to identify whether there exists a relation between two entities that occur in the same sentence. So if there is a relation, what's the relationship? There has been lots of work going on for relation extraction. So in my opinion, these approaches can be classified into several categories. The first approach represents relations using predefined types. So freebase is an example. So in freebase, you have a predefined entity and relation types from a schema. But what's the disadvantage of this approach? So there is no complete schema. It is challenging to design a schema that have all the relations that you are interested in. For example, here, freebase is missing like relation teach at or like or criticize. So researchers have done some work to overcome this disadvantage. So one approach is open information extraction. So in open information extraction, you identify two entities occurring in the same sentence. Then you identify the word sequence between these two entities to represent a relationship between these two entities. So there's also some limitation about this approach. There is no generalization among patterns. So for example, you do not know historian at can imply professor at. So we have done some work to generalize the meanings of these patterns. So what we do is using a generative model to cluster the triples into different clusters. And in the meantime, so patterns falling into the same cluster will represent one relation. For example, here we have two example clusters. So we make the assumption that patterns falling into the same cluster are semantically equivalent to each other. But this has some information loss. Like for example, here you assume professor at is equal to historian at, so you lost some information. Also, like professor at is different from student at. So what we need is a representation that has broad coverage, no information loss, and easy to generalize among these patterns. So here, for example, we allow each single pattern to represent one relation, also each type from a knowledge base to represent a relation. So what we try to do is to generalize these patterns by learning implications among them. We call this representation as universal schema. Okay, here's the outline of my talk. So first, I will mainly talk about universal schema for relation extraction. Then we extend the universal schema to entity types. Then finally, I will conclude and point out some future work. Okay.
So if a new relation shows up in surface form, like blorgs at, will you then sort of slip blorgs at into the existing? Because the idea is that new relations can come up and you can kind of put them into your big graph.
Yes.
Okay.
Yeah. Okay. First, the universal schema for relation extraction. So what exactly is universal schema and how does it work? So here, given a sentence, Peter McLaughlin, the president of National Football League's Seahawks. So what we can do is we can pass the sentence using a dependency passer. Then, like here, from Peter McLaughlin, like this represents a part of the clause. Then from this dependency tree, we can extract a path between two nodes that represent entities. For example, we can extract the dependency path precedent of between Peter McLaughlin and Seahawks. So we mainly use this dependency path to represent relations. Also, we have some knowledge base available to us. So we can find whether this pair occur in the knowledge base. If they occur, then we can identify the relation types defined in the knowledge base.
Are you only looking at paths that have like connect like nouns and a verb in the middle, not any arbitrary path?
Actually, the path is actually learned from your paper. Okay. So we call this universal schema because it's a union of textual patterns and types defined in knowledge bases.
So the entities are noun phrase?
Yes, noun phrase and verb phrases. Just like the content words including nouns and verbs. Yeah. Like between the two nodes in the dependency tree.
But you have to do all this pre-processing first, right? To
Yes.
do all this chunky
Yes,
stuff.
yes,
and then you
exactly.
can
Yeah, yeah. So here's our input data. So we can organize the textual patterns into columns and the entity pairs into rows. Like for this entity pair, McLaughlin and Seahawks, we find their occurrences in the text and mark down the corresponding textual patterns as positive cells. And we also list the types defined in knowledge base as the relations. We also mark down the relation top member or relation person company for this entity pair. So we did the same thing for all the other entity pairs in our data. So here is our input.
Good question.
Okay.
So the text path. So here you go, just president of. Are you only looking at the actual text in the path, or are you using the dependency archetypes as well? You're just not showing it here.
I'm using the X and the words just for ease of understanding. I only show the words. Yeah.
Okay.
Yeah. So what is our final goal? So our goal is to answer users' information need. So for example, user can ask who is the leader of US. User can also ask whether Samuels is a historian at MIT. Also, user can query whether Roy Smith is employed by NYU. So actually, user can query any cell in this matrix. So each cell corresponds to a question whether the column relation holds for the entity pair.
So there's a gigantic number of rows.
Yes, but actually, most of them should be off. Most times, one relation only hold for some entity pairs. Yeah.
I mean, aren't there potentially just a staggering number of rows? You only put a row in if they occur in the same sentence or if they occur
Yes.
in the same database?
So I only put a row here if they occur in the text corpus multiple times, larger than the threshold. I put a row here. Yeah. Yeah.
Do you consolidate different surface forms of the pair?
Sorry.
Do you consolidate different surface form of the pair? So the entity pair, for example, the entity pair Obama US would contain information about Barack Obama, USA, etc. Do you conflate all the surface
You mean
forms?
the coreference thing?
No, do you conflate?
No, surface form, just surface form. Is US and USA and United States the same entity?
Oh, yes, that's a coreference, yeah. So you can do coreference first, to cluster US and USA into the same entity. So what we do is very simple. We just use string match to do coreference, yeah.
So you would have two rows here. So you would have one which would be Obama US and another one which would be Obama USA.
Ideally, you should have only one row, yeah. So that will help you learn accurate.
But to learn paraphrase, you don't necessarily. You can have two rows. If you could conflate it, you're saying it could be better. But your goal is ultimately to learn.
Yes. So depends on how you do coreference, yeah. Okay.
Basically, your network rho is proportional to your training corpus.
Yes, exactly. Yeah. Yeah.
I see. So do you address the issue of generalization? For example, I assume that, as you just said, that you for training set, you identify all the entities and you identify, probably determine what kind of relationship you have. And then in the test set, what if the word expression are different from whatever training data you have, but it's the same entity? Then what do you do?
Yes, so that means for this matrix you will have like half, like you will have half of the matrix observed. Then I will show you my approach can complete the whole matrix. Yeah. Yeah.
But if someone says, I don't know, Obama, United States of America, and it was misspelled or
Yep.
something, would you be able to handle that or not?
Maybe not now. Yeah.
The surface form matching so far.
Yes. Yes.
So it means that the statistics are kind of like spread across. So if I observe, let's say I observe Obama US, and then I observe Barack, leader of USA, they won't be,
Sure.
I wouldn't be able to link those two facts because their surface form is different.
Yeah, actually that's the problem of co-reference. So if you are able to co-ref Barack Obama to Obama and the United States to US, then that should be fill in the same role. Then you will learn leader of is similar to president of. Yeah.
I mean, and like there have been some work, right, where they will use distributional similarity as something to constrain the arguments to, for example, not necessarily be all the different surface forms, but saying that presidents tend to be here on one side and countries on the other side, right? So people have done that too.
So the assumption that this problem is auxiliary to the problem you're trying to solve. So assume that this has been, is solved by some other mechanism, and you're focusing only
Yeah.
on the relations.
Yes, exactly. Yeah.
And then another question is, how do you determine the relations? Given a training set,
Yeah. I will show you later.
I mean, here there's syntactical relations, right?
Yeah, syntactic
it's
relations.
only, it's not, I thought it's semantic here.
I will show you how we get semantics later.
Okay.
Okay. So here, like, how do you do matrix? How do you fill in those cells? Like, so the task actually is matrix completion. So based on the partially observed matrix, you want to fill in the whole matrix. So here I'm showing you that we are able to do this. How? Well, I will show you later. So here I'm showing like the light green cells are predicted true cells and the red cells are predicted false cells. For example, here we can predict Obama is indeed a leader of US. Yeah. So how to do matrix completion based on partially observed data? Okay.
Just about this metric completion. So some of these questions are non-decisive from the data that you have, and some of them might be kind of things that just don't, you cannot apply this predicate to this property. So how do you handle that when you look at it as a metric completion problem?
Okay, I will talk about one model that can handle that can handle like certain relationships can only occur with particular integer types. Yeah. So here, like one approach is matrix factorization. So in matrix factorization, we will learn like a column vector for each column and a row vector for each row. And each cell is determined by the dot product between these corresponding two vectors. Here, in our data, we make another assumption. We assume that each cell is a binary random variable. So based on this dot product, we add a logistic function to convert the score into a probability. Also, in our data, we notice that like some relations occur frequently, some relations don't. So we add a bias for each relation to make the model more accurate. Yeah. So now our problem is how to learn these vectors. So we do not have those vectors beforehand. So how could we learn it? So what is the objective function? We try to maximize the log likelihood of the joint probability of all cells because we assume each cell is a binary random variable, so we can maximize the joint probability. So what about the missing cells? Like we only observe some cells, not all of those cells. So one thing we can do is sample them as negative cells. So now our goal is to maximize the log likelihood of the joint probability of positive unsampled negative cells. Here I will walk you through the learning process. So first we go to one cell. Then for this cell, like if this is a positive cell, we try to maximize the probability to make the probability close to 1. Then we update the corresponding vectors A and V.
Do you handle negation at all? Suppose you saw McCain is not the president of the US. Would there be, so you know that's a 0, right?
Yeah, we don't have negations in our data. I mean, we do not handle negations now, yeah.
So it's all x equals 1 everywhere, or blank.
Yeah, that will give us better negative examples, yeah.
And you don't do temporal, right? Like
No.
Richard Nixon is president. Was president of the United States.
So what does, I was going to ask the same question about negation. What would happen? Would you get a column not president of? Or would you just do ignore it?
Yeah, I think we can add one. No, maybe that is not efficiently, and you add a negation for every pattern. Yeah. That will double the columns, yeah.
What happened in your system? If you get a sentence that says McCain is not president of the United States, will it create a column for that relation? Or?
I think depending on the parser. So the parser may remove the negation. I guess I'm not sure.
If you're using the same rule construction we did, you would drop that.
Okay.
Yeah,
So you get a 1 for McCain, U.S.
So do you apply this?
There are many presidents.
I mean, there is a concept of functional dependency in database, right? If this relationship implies another relationship, you should take care of them so that you get most efficient design. Do you apply this kind of technique so that your relationship selection is going to be most efficient?
I will show you like this approach is general. It should capture the relationship you talk about. Yeah.
Automatically.
Yeah, automatically. Yeah.
So even when you don't handle negation when you look at the text, but for some database, especially I know that for UW's OpenIE thing,
Yeah.
because it's pretty messy and a lot of their relation actually is actually the not thing. So in that case, you'll still consider that because the knowledge base actually has this kind of negation.
At least I know freebase do not have negations. Yeah. So we just take freebase types and our text data. Yeah.
So what's the size of a relationship in freebase?
Freebase now has many, but when we worked here, we just take I think 50 around 50 relations. Yeah, depending on your data. Okay, so we go to. Sorry?
Only 50 columns?
From freebase.
Oh, I mean only these columns. These are 50.
Yeah,
But
so
for these columns,
relations.
they have 4,000 like textual surface patterns. Yeah.
Sorry, I didn't get this. So the relations, they are all relations which exist in freebase.
Sorry?
The relations.
Not all of them are mentioned in freebase. Like some of them are mentioned. So yeah, you may have like blank cells. You don't know whether these relations is true or not in freebase. Yeah, freebase do not have annotations for all the relations.
The non-freebase relations are just coming from counts of the number of parses you've seen that support.
They connect they connect the text. Like President would connect Obama in the US.
Now for the relations that you have, 50 of those, do they contain this kind of redundant relations such as is a man or is a human? One incorporate the other.
No, freebase do not have this relation. Yeah.
No, but in general, in terms of dependencies, do they remove those redundant
I think
relations?
like as a knowledge base, so freebase should have a complete schema. So they try to define relation types that are not overlapping. Yeah.
Do you do a materialized view, or do you just use the raw cells? In other words, if it says presidents Obama is a president, presidents are humans, humans are animals. You just say, Obama's a president, forget the rest.
Yeah,
Okay.
yeah, forget the rest. I mean, I wouldn't be
Griffiths
able
doesn't,
Griffiths doesn't have rules like
It doesn't even have a nested.
No, you'd have to have the separate facets defined, which they often do. So I think you will have that, right? Like for Tom Cruise, you'll have a row that says he's an actor, you have a row that says he's a person, because they explicitly undefined.
Okay.
But there's no difference.
Nowhere have they said that person is actor or actor is person.
No, they have a recommendation for the creator of the thing that you should create that facet, but if you don't do it, you can infer it. So that last could exist.
Okay. So for learning, like our learning requires negative data. So what we do is we can use sampling to sample negative data. Like for example, for one entity pair, Obama and US. So we sample professor at and historian at as negative cells for this pair. So similarly, we try to minimize the probability for the negative cells, make sure the probability goes to 0 instead of go to 1. Yeah, we update the corresponding vectors, professor and historian. So yeah, we go over this matrix iteratively and update the corresponding row vectors and the column vectors. So finally, after many iterations, we will be at a stable state. The vectors are almost fixed. So
you're just sampling the negative ones, not positive ones.
sorry?
You're just sampling the negative stuff.
Yeah,
Okay. Positive ones you use every time, every
Yeah,
sample.
yeah.
And you're doing stochastic gradient descent in the bottom.
Yeah, so this is a stochastic gradient method, yeah. So now, like, finally, our model learns, what our model learns is a bunch of column vectors and row vectors. So how do we do prediction? So go back to our original definition of one cell score. So we just use this dot product and the bias. Then we apply a logistic function to predict one cell's probability. Yeah. So actually, logistic function is mapping a real value to a value between 0 and 1. So it is one kind of normalization. Yeah. So for the vectors, you can see in your learning, you make sure your vectors norm is less or equal to a constant. Yeah, you can. Yeah. Then I will try to explain how this approach learn implications. Yeah. So for example, here, look at this row, Morris and Columbia. This row, we observe two positive cells, teach at and person company. So during learning, we know that each cell's score is determined by the dot product between the row vector and the column vector. So ideally, we should learn that these two column vectors are close to each other in the low-dimensional space. So now go to this row. Here we observe teach at. And we also know that the vector for teach at is close to vector of person company. And this row, these two cells share the same row vector AM. So we can see that the score for person company should be similar to the score of teach at. So that's one way to see that we can learn the implication teach at implies person company. Yeah.
Which way do you know the implication is going?
It's correlation.
Yeah, maybe I should not call this as the implication, just as a intument or
Correlation.
Correlation. Yeah. So here I will show you more mathematical details about this learning process. So we assume each cell is a binary random variable. Here are the definitions for this cell score. Then yeah, we made this assumption. So our objective is the data likelihood, like the joint probabilities of all the cells. Then we can use the log likelihood and add a regularizer to this objective function. then we can get this gradient. So our learning process is a stochastic gradient optimization. For each cell, we apply this gradient to update the parameters. Then
Maybe I should talk about this offline, but how does the independent assumption work here? Because the model is saying they're not independent, right?
you mean, yeah, we assume each cell is independent of another cell, yeah.
But the model itself is doing the opposite. It's
The
linking them
model
together.
is not doing the opposite. We just see, yeah, you are, yeah, I can see, yeah, why you say this. You are like, we are assuming like one row share the same row vector, yeah, one column share the same column vector. But we still make this independent assumption,
Well, it's
yeah.
independent given the rows and the columns,
Yeah.
right?
Yes, yes, yeah. So maybe some thoughts about learning. Like for this objective function, we maximize the log likelihood of positive and sample negative cells. Then people may think like, why are there some alternative ways to? Actually, yeah, we do not know which cells are negative. So are there alternative ways to set up the objective function? So we can choose ranking-based objective. So like it's intuitive to rank the positive relations over the missing cells for one entity pair. So this is actually row-based ranking. Also, in some cases, it's useful to rank entity pairs with respect to the relation. So that is column-based ranking. So here I will show you. So yeah, here row-based ranking. So each cell is indexed by a tuple and a relation. So for each tuple, you rank the positive relations over the other relations. Also, for each relation, you can rank the observed entity pairs, observed tuples above the other tuples you haven't seen. Similarly, you can make the Bernoulli assumption. So the ranking, like the ranking of a pair, can be drawn from a Bernoulli distribution. Then you can apply this maximum log likelihood on pairs of cells. Okay.
What do you do with the fact that, I mean, there's some bias in the data, like let's say you have, some relations are much more mentioned than others.
Yeah, that is one thing is the bias. Like some relations occur more frequently, so I have a bias term for this relation. Yeah.
But it means that those types of ordering constraints are like automatically satisfied. You know, like without looking at T, I can tell you that CEO of is more frequent than manager of, without looking at which tuple it applies to, just because. So this means that then if you do some kind of constraint optimization about this, you will get a lot of satisfied constraints, not even looking at the tuple, which means that you don't exploit this to learn the tuple, right? So what would you do to kind of correct this? Or maybe it's not a problem, you know, I don't know.
It depends on how you sample the negative data. I think here, like for each entity tuple, then you have some observed positive relations. Then you sample the negative relations. When you sample the negative relations, you can have many strategies. Like one thing is if the relation is frequent, maybe you sample them more. So that will give you more negative examples about that relation. So that means in your prediction, that relation won't occur more times. Yeah.
So you play with those type of kind of prior on the negative sampling.
Yeah, yeah.
If you've learned this way by ranking, then does that mean you can no longer ask for a given cell what is the probability of that relation? Now you can only compare two cells?
Yes, you are right. So in this ranking scheme, you can only see one thing is like one thing has a higher score than the other. Yeah. But in our experiments, we still apply the logistic function because here we still get a score for one cell. Then we can apply a logistic function to get. To convert the score into the range to 0 and 1, yeah, just for evaluation, like, yeah. So here, so factorization model is successful, but it still has some disadvantages. So that's why we introduce other models. So factorization model fail to model localized structure. So what do I mean by localized structure? So some columns, like some patterns that occur fewer times, but they are good indicators for other columns. So I will give you an example. Like here, champion from. So this pattern doesn't occur many times, but every time it occurs, it co-occurs with person nationality. So the factorization model does not capture this. So we need a model to capture this localized relationship. So we introduce the neighbor model. So the neighbor model is similar to a classifier. So here, look at this highlighted cell. So this cell is, we try to predict whether person-company relationship hold for this entity pair. So we can use a classifier. So we take this person-company as a label, then other patterns occurring in the same row as features. So we can build an exponential family classifier to model this. It is shown in collaborative filtering that whether it is a factorization model or it's a neighbor model, neither one is superior to the other. So we can combine these two models together to model one cell. Here in this formula, this term is a factorization term, then the bias for each relation, then the neighbor model term. Okay, selectional preference. Yeah, so people already mentioned here, like relations has selectional preferences. Like some relation types, they are picky about their argument types. For example, here, professor at, means the first argument can only be person. The second argument can be university or institute. And this president of, the first can be person, second can be organization, country, sports team. So we try to incorporate this information into our model. So what we do is instead of using one vector for one entity pair, we use two vectors. So these are entity vectors. The first, we have one vector for this Morris and another vector for Columbia. In the meantime, we can represent this relation using two vectors, one corresponding to each argument. So we can add this term to the final score of the cell.
You add the dot products.
Yeah,
two
dot products.
I would have thought you would have done a tensor and you would have done
yeah, I'll talk about tensor later. Yeah.
Oh, okay.
Yeah.
So
People try the tensors. Yeah.
What is the difference between adding these two inner products versus just having longer vectors?
Mm-hmm.
So this try to capture that some entity can only go with some particular relations. Like I just showed, like the person entity goes with the president of or professor of. Then if the second argument is a university, then university can only go with professor of.
I understand that, but eventually the mathematical object that you end up with is equivalent to just concatenating the vectors.
These two vectors could be different. Yeah.
So I think Morris is tied. So if Morris shows up somewhere else, then so it's like having a longer vector where the halves are tied.
Oh,
between
I see.
them.
I see. So it's a vector for each entity, and the entity can repeat.
Yeah, actually there are many ways to do this. Yeah, I will talk about later. Yeah, like some other alternative ways to factorize this data. Yeah.
But I mean, maybe this is John's point, but learning the Morris vector and the V1 vector separately from the Columbia V2 vector, it seems like you're learning that Morris is, what's the relation?
Professor at all person company.
Morris is a professor somewhere, and then separately learning that someone is a professor of Columbia, but it seems like now you'll get all all pairs are gonna end up.
I know. Yeah, yes, you are right. Yeah, so there is a tensor model for this. Like you have 3 vectors, one for the source entity and one for the relation, one for the destination entity. Like tensor is one way to solve this. Yeah. So, but this is one way.
But you didn't really run into that problem. Somehow it doesn't really have that problem.
I will show you in our experiments. So this model is not. Does not improve the performance a lot. Yeah.
Okay,
Yeah.
But it's not worse.
It's not worse. Yeah.
Okay,
Just
so-
we are still exploring ways to represent entities and
Yeah.
relations jointly. Yeah.
It's a kind of type bias, right? So if Maurice has a vector which is a human, he's more likely to be a president, a CEO, a teacher, whatever, than if he's a university.
It seems like you need both. Like it seems like this helps with the types and making sure that Morris is only on the relations that want persons. But it seems like you lose the tying of Morris and Columbia together. So it
Yeah.
seems like you kind of want both.
So the combined model can like overcome this disadvantage a little bit. Like here we have a combined model. So the combined model have all of these terms, like the factorization, the bias, and the neighbor, and this part. So yeah, you have everything. Okay, now I will show you like how well this performs. Yeah. So we are working on text data and knowledge base. So for text data, we use New York Times. So we do some pre-processing, like NER notation, dependency parsing, then we extract the triples. So each triple has 2 entities, the source entity, the destination entity, and so then there is a dependency path between them. So for knowledge base, we use Freebase, which is a collection of entities and relations from Wikipedia info box. Also, they add some human annotations.
What is the scale of this? Like, so you count, so basically to surface, like from the text, so from the New York Times, to surface a triplet, you need the entity to occur a certain number of times, the destination entity to occur a certain number of times, and maybe you have a way also to kind of counting dependency path.
Yes, exactly, yeah.
So you have like kind of threshold and depending on the
yes.
threshold you can vary the size of your matrix and the amount of support you have for every pair. So do you play with that, or do you fix it once and for all?
So for the pattern for the dependency paths, like you can have many dependency paths. So we just restrict our paths length. Maybe the length should be smaller than 10 or smaller than 5. Then you pick the path. Then for the entity pairs, yeah, they have some frequencies. You cut them by frequencies. Yeah.
Oh, you just restrict on the length of the path. You don't specify a number of occurrences for a path?
Both,
As well?
both. Yeah. Then we carry out some experiments. So we split so for the whole matrix we can split them by the rows. So we have some train tuples and test tuples. Then we can do some predictions. For the test tuples, we can predict their Freebase types. I'll show you what our approach can do and what we can evaluate. So first, we can discover, maybe I should not say implications or correlations. Then based on some observed patterns, we can predict unseen patterns. Then we can predict relation types and surface patterns. So here I will show you some example predictions. For example, here, the second one. So this Miller's replacement Mark, then we can predict Miller is replaced by Mark or Miller is succeeded by Mark. For this row, for this entity pair, like one person's mother is Claudia, then we can predict these patterns and also the relationship person-parents. Yeah.
So when you did this test, you just blanked out half the matrix during training and then used the predictions of the...
What do you do with kind of collision, like let's say Smith
Samantha
and John. Let's say you have 2 entities, the pairs are Smith and John, They will have like every possible relation you can find in the New York Times, I'm pretty sure. Because basically you kind of collide different entities into the same surface form.
I see. Yeah. Smith and John are very common names, first names. I think in my processing, I did one thing. If there are more than like maybe 100 or 50 patterns occur between two entities, I don't like this rule. I think it's junk. Yeah, so. Okay, so these are some examples. Now I will show you like some numbers to show our results. So here is our evaluation setup. So we compare against the other approaches for relation extraction, mainly distant supervision approaches. Like this is the first approach about distant supervision proposed by Stanford. Then the second is distant supervision using some clustering features. I use generative models to produce these cluster features. The third is another distant supervision-based relation extraction system. So for evaluation, what we do is, so it's challenging to evaluate the whole matrix. So we sample some entity tuples and we pick some relation types. So we rank the entity pairs with respect to these types. So we measure the mean average precision. Also, we want to evaluate the predicted surface patterns. So we randomly sample some surface patterns. Also do this ranking to get the recall and precision curve.
So how do you handle, did you do any labeling?
Yes. So here, for example, if we pick this person company, so even though freebase has this relation, freebase is not complete. So what we do is we from this sample the 1,000 entity pairs, we label whether this relation is true or not. Yeah. So these numbers are compared against this human annotated data. Yeah. So here we show that.
You kind of pick the n best for each model and get them labeled.
So we have 200,000 test tuples, but we pick 1,000 entity tuples. So in this 1,000 entity tuples, so we use different systems. So different systems will rank these 1,000 tuples differently. Then we pull them together to get something to annotate. We only annotate those pulled things. Yeah.
And these results are just on the annotated.
Yeah. So we can see our approach achieve better performance than other approaches.
Give a sense of the error bars? Because 1,000 is not, you have 1,000 cells.
No, 1,000 entity tuples. Then,
so 1,000 rows.
Yeah, 1,000 rows. Yeah. So here I show you that so our approach can predict surface patterns. So here I show you the results of like the curves for predicting surface patterns. So here the neighbor model is the red line. We can see that the neighbor model performs worse than other models. And like the factorization model and the combined factorization and neighbor model perform similarly. That are the green and the blue lines. Here, we can see that adding the entity model helps a little bit in the low recall area, but does not help as recall increases. That's the purple line. So there are still like challenges how to model the entities and the relations. Yeah.
How many surface patterns was this?
Sorry?
And you said it's for some surface patterns. How many?
These are 10 because you need to label them, so you do not have any good answers from knowledge base. So we just pick 10.
Do you have a sense of the error per kind of cell which is populated? Like let's say I have two cases. I have a pair of entities for which I have like 100 relations which appear in my database, and I have one for which I have 3. I expect to be much worse on the one where I have 3 because I will have less data to kind of build what vector I should learn. So do you have a sense of error per kind of supporting point in the data?
I don't have a statistic for that. Yeah. But yeah, we try to model the intuition that like for an entity pair, at most maybe you should have like 10 relations or some relations. You couldn't have like more than 50 or 100 relations. Yeah, if we could model that, then it could be more accurate in learning. Yeah. Okay, so related work. Yeah, here I will show you. There are many factorization models for relation extraction. So one is generative model. You can choose the infinite number of topics. So there's the tensor model for factorizing relation. So here they represent a relation as a matrix. I will show you the figure in the next slide. Then there's tensor and translation models. So here, like you have 3 vectors, one for the source entity, one for the relation, and another for the destination. So here they make the assumption that this source vector plus the relation vector should be close to the destination vector. Also, standard tensor decomposition can be used for relation extraction, a canonical tensor decomposition. Basically, each cell is a tensor product of these 3 vectors. So here I summarize all these models and show their number of parameters. So K is a number of low dimensions. So here the figures somewhat show what they do. So the first approach, they represent each entity as a vector, then each relation as a matrix. So in this approach has many more parameters than other approaches because you want to represent each relation as a like k to the square using these many parameters. Yeah. So all other approaches represent a relation using one low-dimensional vector. Yeah. So our approach represents one entity pair instead of one entity. Yeah, in the factorization model. Yeah. So there are some related work in collaborative filtering. There are many strategies for handling negative data. Then, like this logistic loss is first presented by Michael Collins. Also, our work is related to entailment. Like people use logic to represent implication, represent entailment. Like the first 2 approaches, like they have strong representational power, but the first approach is limited to answer questions in one domain. And second approach, it is challenging to learn. So the third approach is presented by U. Washington, but they use some statistics to discover the inference rules. So our factorization approach is more principled. Here, like many embeddings gain lots of large amounts of attention recently, like neural network language models, and also deep learning for NLP. Also, I think here at Microsoft, like polarity LSA is related to our work. It's also doing like factorization. Okay, so now universal schema for entity types. We know that entity types are useful for relation extraction and knowledge-based construction. So predefined fine-grained entity types are needed, but however, we have some challenges here. There are debate about granularity. It's subtle to label boundary cases and costly to obtain training data. So we can extend the universal schema to model entity types. So similarly to relation extraction, we extract unary patterns for entities. For example, here, maybe for Coca-Cola, you can extract a drink Coca-Cola as this pattern. Also for another music group, you can extract this appellative structure group as a pattern. We also know that like phrase has some types for the entities. We can extract those too. So here list some example types, like executive, broker, company, senator, and so on.
So are these derived from free base?
No, these are derived from our text. So yeah. So here I can show you more examples. Like here, House of Pin, you extract the pattern rap group. Also albums by House of Pin. So you can organize the data into a matrix, then do matrix completion again. Yeah. Here we can use the models presented earlier for relation extraction, a factorization model, the neighbor model, and also the combined model. Notice that in integer recognition, besides these unary patterns, you can have other features. So you can also incorporate these features to enhance the performance. So I will show you experiments on tabs. So here.
See how this gives you the types. The
Okay, here. So for example, the appellative structure, like you will see somebody, an executive of, then this executive could be extracted as a unary pattern. So this appellative structure could be a tab. Like usually you see Bill Clinton, a politician, or a senator. That senator or politician could be tabs. Yeah. Yeah.
Is it the exact same algorithm where you replace the entity pairs by single entities?
Yeah, exactly, yeah.
But not all the columns are here. Because I could sip something. I could sip professor. I don't know. So, but the whole point is that some of the columns are just there to help you determine the unary types.
Yes.
I see.
Yeah.
So what is this material? And what do you call schema? Schema really, it just means that you have how many attribute you have, what kind of type of attribute you have.
So my schema is a universal schema. That means anything can tell you something about one entity or one entity pair. That is a schema. So here, like you can see, sip X is one schema, then a drink is another schema. It's another type. You can see, yeah. So here, show you some example predictions. Like here, you observe financial, then you can predict investor, magnate, or philanthropist. Yeah. Here, analyst, economist, and expert. Then here, somebody can sing. You can predict he must be a singer. But sometimes you may get some errors, like sing usually co-occur with baritone, but actually he is not a baritone.
It seems like you show two models and they can do the same thing, right? So they could be like one single column with the either relation where I have like Jack Lion, comma, financier, and it should be I in the either column. Then you have like this kind of unary view where I have a single matrix where this is only deal with either. And I have so what is the kind of, so now I could choose between both, right? I could choose between having like n matrices, one per relation, or like
one for this, yeah. I will show you in in future work section. Yeah, you can combine these things together. Yeah. Here, we carry out experiments on WikiLinks data. So that is a collection of web documents. So it has a collection of entities and their mentions from web pages. some of these entities are linked to freebase, so we get some freebase text, but we do not have NER tagging and dependency parsing. So we just take neighbor words as column, like for example, basketball player, Baron Davis, then we take basketball and player as columns. So on this data set, we measure the F1 using different models. We can see that the combined model is better than neighbor model and the factorization model alone. So some of these numbers are low, so I did some error analysis. Here, for some types, we have fewer training examples, like food, cheese. We have only about 140 training examples out of like 300,000 total training examples. Sometimes the features are not sufficient enough. For example, you will see like some entity co-occur with vaccine, but actually it is treated this guy with vaccine. So our system wrongly labeled X as medicine drug. Also, this Q is a keyword for disaster, but actually criminals is the entity. It should be a person, should not be an event disaster. So we can do one thing is using a coarse-grained NER. This can fix this problem. Also, we can use dependency paths. But on web data, you know, dependency path is maybe not accurate. So sometimes it's due to confounding types, like event disaster is close to terrorist event or event accident. Yeah.
Is it maybe a kind of data? You were to have more data, this would be solved?
I think even if you have more data, you need to design your columns very well. Like this treated X with vaccine. Maybe you should use like n-gram features, like you use treated or with vaccine instead of using only one word vaccine.
So, question. So it looks like you're trying to uncover an ontology here of entity types.
Yeah.
So why not use something like WordNet that has ontologies already built in as training?
Yeah, WordNet is. WordNet has larger coverage, and but some people show that on the particular data, you have some tasks. WordNet may not help you as much as you expected. Yeah. If you do just your own clustering, that may give you better performance than using WordNet. Yeah.
But if you use both, is what I'm asking. If you could incorporate the
Yes.
information in
Yeah, that means besides this freebase thing, I can use WordNet as well. Yeah. You are right. Yeah.
Does this approach have the same limitations as the previous, where you could learn a correlation that like singer and songwriter tend to be the same, but you couldn't learn that, you know, vaccine is a type of drug, but not all drugs are vaccines? Or
That has the same limitation. Yeah.
Or baritone is a kind of singer.
Or baritone is a type of singer, but not all singers are baritones.
Yeah. Okay. So, we know that researchers have shown that entities can help relation extraction. So here we want to show that our predicted universal schema entity types can also help relation extraction. So we add the predicted types as features in the neighbor model. So we compare against these baselines, predicted NER, predicted freebase types, and our predicted patterns. So here, the first three rows are relation extraction without these predicted types, and the last three rows are relation extraction with these predicted types. So we can see that adding NER hurts the performance, so the coarse-grained is not enough. And we also observe that using predicted freebase types has similar effect as using predicted patterns. So this suggests that the patterns could be replacement for freebase types. Yeah. So now I go to the conclusion, and talk about some future work. So to summarize, we present universal schema. So this picture captures the whole idea. So you observe some cells, then you try to complete the whole matrix. So this representation, we allow single pattern to represent a relation. Also, we gain generalization by matrix completion. We also introduce other models to compensate the disadvantage of factorization. So for future work, one thing is the joint entity and the relation instruction. So we want to model relations, entities, and the selectional preferences. For example, if you know somebody is a writer, then he tends to participate in the write relationship, like between author and the novel. So one representation is for the binary relation data, you can have entity pattern. Then like you can do two things. One thing is you use a tensor, like ES stands for the source entity, and ED stands for the destination entity. So you can use a tensor that has three things, or you can use a matrix that has two things. Also, you have the entity attribute, that's the unary relation data. So each entity has some attributes. So those attributes are unary patterns. So we can do a joint factorization. So here the likelihood is, so the first part is a tensor product, like you represent the binary relation as like entity relation tensor. The second is about the entity themselves. So entity has some unary patterns. So actually for the first part, you can do two things. Like here, you can use a tensor at the same time use a matrix. So you factorize them twice. Then this is information about the entity and their unary patterns. So this is one way to do joint factorization. Another direction is incorporating constraints. For example, you know that both Seahawks and Patriots are football teams. So in your model, you can make sure that the row vectors for these two teams are close to each other using the last term. Another interesting direction is infer multi-hop relations. Like if you know A is brother of B and B is parent of C, then A should be uncle of C. So how do you do this? One model is so besides the original like entity pair and the relation matrix, you have another tensor. So this tensor will take care of the patterns. So the tensor will, so the brother of will get a vector, then parent of get another vector, uncle of has another vector. So each cell should be the tensor product between these three vectors. Yeah.
So I thought brother of that relationship typically is a matrix rather than vector.
I mean, you take brother of and parent of and uncle of, you build another tensor of using these three patterns. Yeah. Here, like some strategies for sampling negative examples, we can get inspirations from the like collaborative filtering literature. Also, in natural language processing, people have presented like a contrastive estimation for get the neighbors. So, yeah, we can explore in this direction. Another problem is make factorization scalable. So we can do parallel stochastic gradient optimization for matrix completion. Like somebody also have some work on this. Lastly, I will mention some of my other work on relation extraction. So I explore generative models for relation extraction. So we extend the standard LDA to model to generate the triples. We also use type LDA to model the selectional preferences. Also, so use patterns to represent relations. will have some ambiguity, like A beat B could be Obama beat Romney, could be Seahawks beat Brownox. So we want to separate these two entity tuples, so we design a generative model to do this. That's all. Thank you.
Yeah, so for the last example, A, B, B, so this is really just to disambiguate semantic. But if you actually can do some pre-processing saying that B has two types, one is, that B, the other is the other B.
So our approach is like a two-stage approach. So at the first stage, for each pattern, A beat B, then we try to we collect all the entity pairs co-occurring with this pattern. Then we cluster these entity pairs into different clusters. So each cluster represents one sense.
I see. So rather than having campaign B and sports B, treat them as two different relations, then you solve the problem.
Yes, exactly. Yeah.
I have a question out of curiosity. The main focus and motivation here is coming from text, for analyzing text and finding entity. But can you apply the same techniques to other types of data, for example, images? So I can learn things like cars have windows, and cars ride on roads, but using only images or video or visual signal as a source as opposed to textual signal.
I think you need to have two sources, like one image signal and the corresponding text signal. I mean, without prior knowledge that car run, if you do not, you should have some prior knowledge of knowing that car runs on roads. Then otherwise all you can do is first you build a knowledge base from the text. Then you apply this knowledge base to improve your image recognition. Yeah. Then if you know that from your knowledge base, cars should run on roads. Then in image segmentation, if you detect a car, then you should have some higher probability to detect the road. Yeah. I think in CMU people are working on, like CMU has a never-end learning system. They also have another, like some system about image. They try to combine this text and image thing together. Yeah.
Right, let's thank them again.
Thank you.